Today, we start part C of Module 2, Basic Asymptotic Notations. There are several asymptotic notations, but we just learn those are commonly used, the basic asymptotic notations. C.1, Introduction to Asymptotic Notations. First, let's look at how to compare two growth functions. In the previous video, we saw we use the limit of the ratio of two growth functions. So we calculate the limit so we can do the comparison. Here, the title here, limits of two growth functions. Actually, we can say limits of ratios of two growth functions. All right, so then let's look at the cases. When we consider a limit of the ratio of two growth functions, how many different cases do we have? The cases here, we look at the possible different values, the value types of the limits. All right, here I summarize, I have 4 cases. So let us look at these 4 cases. First case is 0, the limit equals 0. So that is a, pretty common case. Second, constant C here, non-zero constant C. Because the first one already we look at the 0 case. So the second one, we should avoid 0. We don't include 0 in the second case. But for constant, non-zero constant C in our algorithm context, because when we compare two growth functions, we expect two growth functions, they both have positive values. Because typically, when we use a growth function, we measure the number of basic operations. That should be a positive number, right? So the values for all the growth functions should be positive. So then the C also should be positive. Positive constant. So we can call in our special context, not the general context, in our algorithm specific context. So the constant C should be a positive constant. So then infinity, another case, infinity, it's possible. The limit is infinity. And then the fourth case, none of the 3. Is that possible? None of the 3, other. Actually, later we will see the limit does not exist. So there is a situation the limit does not exist. It's also pretty common. Pretty common, this case. So all these 4 cases should cover all the possible situations we have in our algorithms discussion analysis. All right, then let us do some more discussion on these 4 cases. First one, we want to consider, when we do the comparison, we need to look at the result, right? The possible results. These 4 cases correspond to 4 possible results. Case 1 corresponds to order of growth of f of n is less than order of growth of g of n. In other words, the g function grows faster than f functions. Yeah. So think about that. The ratio equals 0. The denominator dominates the numerator. Yeah. So you can, use your intuition to understand. Yeah. All right. Here, you may ask me, what's the meaning of order of growth? Here, let me give you a simple explanation. What is the order of growth? Yeah. Typically, when we look at the growth function, we want to take the dominant term, right? So after we take the dominant term, we ignore the leading constant of the dominant term. Yeah. So we try to make that part as simple as possible. All right. So typically, after we do that kind of simplification, so we end up to get a function in this form, n to the alpha power. It's a power function. It's a power function. All right. Yeah. N to the alpha power function. Yeah. And this alpha, typically, it's a positive number. Yeah. Because when it is a positive number, it grows, right? Yeah. So the function value will grow, the growth function. Yeah. So then this alpha corresponds to the concept order of growth of our growth function. Yeah. All right. So that is the first case. The second case, order of growth of n equals order of growth g of n. Here you can see when the limit of the ratio is positive constant, then we get here case number 2. These two growth functions, we treat them, they have the same order of growth. Yeah. Because the constant value does not matter here. Yeah. Because here we look at a positive constant c. What is that value? Right? You may ask me, how big? Yeah. Or how do we characterize those positive constant? We don't do characterization here. Yeah. Whatever value it is, if only it is positive, then it does not affect order of growth. It does not affect order of growth. See? Yeah. Here, try to understand this point. Yeah. Because sometimes the C could be 1 million or 1 billion. Sometimes the C could be a very small number, 1 millionth or 1 billionth. So think about that. Yeah. In all those possible positive C values, they do not impact the order of growth. So think about that. Okay? So that may not quite be compatible with your intuition, right? Yeah. All right. Because here we do very abstract analysis. Very abstract analysis. Try to get used to the abstract discussion for this topic. Yeah. All right. So next, case number 3. Order of growth of f of n greater than order of growth g of n. Yeah. Just the opposite of case 1. Yeah. Because case 1, if we take reciprocal upside down, we get case 3, right? Yeah. Yeah. So you can see, we switch position of the numerator, denominator, we get case 3. And case 4, quite different, because the limit does not exist. Yeah. In this case, we need to find a new way to study it, because we cannot use limit method. We cannot use our techniques calculating limits in calculus for our case number 4. Okay, so we need to find a different method. So we will see that method. Yeah. All right. The limit way has limitation. Yeah. So we need a new method for case number 4. Yeah. All right. Yes. Yeah. Yeah. So we will see that new method. Yeah. All right. So our objective, because when we compare the order of growth of 2 growth functions, even if the limit of the ratio does not exist, we want to do the comparison. We want to get some comparison result, right? Yeah. Is it possible? Right? Yeah. Yes, it is possible. Yeah. So we will have other techniques to solve this problem. Yeah. All right. Before we go that discussion, yeah, here we need some compact notation for these, let's say, the first 3 cases. Yeah, case 4, because still we need to find a new way to study it. For the first 3 cases, we want to use compact notations to describe. Otherwise, if we do not introduce good notations, it is not very convenient to discuss the first 3 cases, right? You need to use a lot of words, a lot of sentences, so not very convenient. Here, yeah, let's use some compact, simple notations here. For case 1, we use this notation. F of m belongs to little o of g of m function. Little o, here you can see, we introduce this little o notation. Yeah. What's the meaning of little o of g of m? Yeah. This is the meaning. Order of growth of f of n is less than order of growth of g of n. So you can see this long sentence, we do the abstraction to make it as a relatively short notation. F of m belongs to little o of g of n, right? Yeah. Second case, we use the big theta notation. Big theta. Okay? Yeah. All right. F of m belongs to big theta of g of n. That means these 2 functions have the same order of growth. That's simple. All right. Case number 3, little omega notation. Little omega notation. See? Yeah. All right. So that's the first 3 asymptotic notations. So we call asymptotic notations. So why we call asymptotic? Yeah. Later, when I talk about the definitions, you will get idea why we call it asymptotic notations. Yeah. All right, so next, so let's look at how do we study case number 4. Right? Yeah. Here, we want to find a good method to study, to compare 2 growth functions, but the limit of the ratio does not exist. Yeah. We will use upper bounds and the lower bounds to study. Upper bounds, lower bounds. In this way, we can avoid taking the limit of the ratio of 2 functions. Yeah. How do we use upper bounds, lower bounds? Very simple. So let's look at the details. Yeah. How the function G of n, we know, usually we use a growth function, right? G of n. Yeah. Usually a simple function. Yeah. The G of n, the denominator, usually we want to use a relatively simple function. Yeah. So like n squared, n log n. So typically we use that kind of, special functions. Yeah. And f of n could be a complex function. Yeah. F of n, yeah, because we want to study the order of growth of f of n. So the f of n could be relatively more complicated. Yeah. All right, yeah. So then our idea, our goal, we want to use some constant multiples of g of n to approximate f of n. Now, approximation, because f of n is too complicated. It is very hard to see how fast it grows. So then we use relatively simple g function to approximate the order of growth. Yeah. But the question is, how do we do the approximation? Yeah. Upper bounds, lower bounds of f of n using constant multiples of g of n. That's the way. Yeah. So let's look at the formula. Yeah. Specifically, can we find two positive constants, C1 and C2, one for lower bound, one for upper bound, C1, C2, such that this inequality holds? C2 times g of n less than or equal to f of n less than or equal to C1 multiple of g of n. So this is the new criteria we use to replace our old limit of the ratio of two functions. In this way, we can avoid the limit. In this formula, you cannot see the limit, right? So that means even the limit does not exist. We can use this inequality to compare the order of growth of these two functions. Yeah. All right, here, yeah. So the advantage of this method works no matter the limit of the ratio of two functions exists or not. Okay, yeah. All right. So here, it's the abstract discussion. Abstract discussion. Yeah. So I hope you can understand, all these abstract notations, concepts. Yeah. Not easy, but we try to get used to it. Yeah. All right. Next, I want to introduce another commonly used asymptotic notation. Actually, it is probably the most popular asymptotic notation. It is called a big O notation. Big O notation. Yeah. So we need to do, very detailed discussion. Yeah. So let me give you the definition, formal definition. Yeah. For a given function g of n, the notation big O of g of n represents the set of functions. Yeah. So this notation is a set of functions. All right, yeah. Here we use the concept set, a set of functions. Yeah. F of n that satisfy the following conditions. Yeah. So what are the key conditions here? Yeah. The condition is pretty long. Right? There exists some positive constant c, and some non-negative integer and 0. This one will require integer, non-negative integer. C, just positive. Yeah. such that the condition f of n less than or equal to c multiple of g of n. Here you can see we only use the upper bound side. We don't look at the lower bound. We just look at the upper bound. Okay? Yeah. C multiple of g of n is used as an upper bound of f of n. Yeah. All right. So more description. Yeah. This inequality holds under a little more condition. So what's that condition? For all n greater or equal to that n0. n0 we treat as a starting point. Yeah. When n, variable n, the problem size variable n is greater than this some specific starting value, this inequality holds. Before this point, we do not require this inequality true. We do not require it. Yeah. All right. Here, the meaning n0, it's pretty special. Yeah. So its value, when we choose it, it's pretty special. Yeah. So what's the meaning of this one here? n0, you have freedom to choose n0. Okay? Yeah. You have a lot of freedom. You can choose this n0. A big number, small number, you can choose. Yeah. A lot of freedom. Yeah. But there is a condition. After you select it, you have to fix it. That means after you select 1 and 0, then you cannot change. Okay? You have to stick with it. Okay? When n problem size grows, you always use this n0. Okay? You can never change. The first time when you select it, you should select the one that is good enough. All right? Yeah. Because you cannot always change this value. All right? Yeah. Okay. So if you can satisfy this condition, then you can use the big O notation. Here, the special property of this n0, we use another special term for it when n is sufficiently large. Yeah. Frequently, you see the wording when n is sufficiently large. So you may ask, what's the exact meaning of it? Sufficiently large, right? Because it is too vague. If you only understand it from English language, you will feel it is vague. It is vague, right? Sufficiently large. But if you look at this definition gives you precise meaning of sufficiently large. Yeah, here the condition. We use n0. The way we use n0, that means sufficiently large. All right, so we finish C.1.